he did his PhD from both the university, but after that he has done multiple postdocs, one in South Africa. But did you go to South Africa?
Yes, yes.
Okay.
Yeah.
I thought you were in Paris.
Yeah, it was partly Paris, partly South Africa.
Paris and South Africa with Henning. And after that you...
Before that I was in Spain, Barcelona.
Right. In Spain, with whom?
Oriol Serra and Camino Balbuena,
Okay.
two advisors.
So now he will be giving a talk on homomorphism model, navigational queries of graph databases.
Yeah, thank you, Shagnik. Okay, so this is about some applications part of the project, and I want to show you how graph homomorphisms is very related to databases. And I mean, I myself, I'm a graph theorist and graph algorithm person, so it will not be too technical about graph database, but hopefully, databases, I gave you some idea of how our homomorphism work is related to this topic. And to create maybe some interesting things for different communities. Okay, so the classical model of a database. Okay, so first of all, what is a database? Those of you who know about computer science know. This is basically just a way to store large amounts of data, right? So typically when we have applications in the internet or something like that, we need to store all the data. And for that we need some huge computers that will have some storage for getting all that data, right? And the classical, so there have been a lot of theory since the 1960s, 70s especially, about how is the best way to store all this data. And the main point here is to organize the data so that we can retrieve it properly. There are lots of different aspects. Also the safety should be regarded, etc. I mean, I'll not speak about these technical details. Yes, so this is one classical way to view such a database. So it consists of tables. It's organized in that model. So each of these three blocks there is called a table. And what is one table? A table will consist of different columns like that. That will be some kind of attributes, okay? And one entry of data in that table is one line, okay? So for example, in that table, this line is one entry. So this database here is about some books. So that entry will collect some information like the title, the author, etc. Okay? So this model, I see, yeah, in the 1970s has been studied a lot. Okay. And what is a query in that database? A query is just a way to, well, inquire the database and return some piece of data. Okay. I mean, here's just an example of a very classical query language when you have this kind of queries, which is called SQL. So it will look like that, for example, here, in that line. And just ask, I don't know, for example, all the entries which have author such and such, or all the entries which look like this and that. Okay, so this is a query. So now, what about graphs? Okay, let's go back to these tables actually. I mean, one way to view this in a combinatorial sense, I mean, this is how I view it. I actually view this like more like a hypergraph. So you can imagine that all these pieces here are nodes or vertices, okay? And that one line is a connection between them. So it is, you can see it as a hyperedge. So it's just a set that connects these things, okay? But now we like graphs, right? So what about viewing it as a graph? Well, you can do that too. And there are so-called graph databases. So they're just these kind of databases where relations are binary, meaning that the entries are the vertices. So for example, this is one example here. Okay, so the data is stored in a graph. And then instead of being connected in like tuples, they are pairwise connected, okay? So this graph, for example, represents some data. I think this is taken from Wikipedia. So these are some artists, and as you can see, this is a directed graph, and which is labeled also. So it's a directed edge-colored graph. And so there is some information on the vertices, okay? So there are labels on the vertices, and there are labels on the relations, so on the arcs. okay, that connect the pieces of data. Okay. And these graph databases actually, it turns out, I mean, I learned about this maybe about 1 year ago or something. So a lot of people use this actually. It's very, very trendy at the moment and very fashionable in some sense. Because graphs are such nice structures. Also, they're very related to some of these huge companies that you know of, like Google, like Facebook and all of this. They're actually based on graphs, so they do a lot of graph theory actually. So there's a lot of actual database systems which are using graphs instead of the, let's say, classic model of relational database that I showed before with these tables. Nowadays, lots of them use graph-related things. Okay.
So in a vertex, you store one line of information.
No.
Or the line of information is broken into columns in a vertex.
Well, it's more flexible than that. So you can imagine that only one. This is a vertex. Okay. And that there will be only one edge from that vertex to that vertex, okay? And then will be one vertex to that, etc. One edge to that, okay? But you can do whatever you like, and there's more flexibility in that model in some sense. Okay.
Here you don't have to store data about data, metadata.
Sorry?
Metadata. There is a conception in metadata.
Yeah.
Relational database system.
Mm-hmm.
Data about data. What is the numerical length of that data?
The length of the data? Sorry? No.
RDP base.
Yeah.
There is a data dictionary concept.
Okay. Well, I don't know about that. I mean, I'm not very. I don't know much about graph database. I mean, about database in general, right? I mean, this is just a motivation to show why graph theory is. It's just to give some motivation.
So, in the previous databases,
Yes.
it was a fixed rule.
Sorry?
It was not so flexible. There was fixed rules to do it, and here you can have different kind of.
Well, I mean, both are flexible. I mean, you can create tables. You can. But yes.
Can you have reverse arcs? Yes.
Yeah, everything is possible. I mean, maybe every system has its own restrictions, but I don't know what. I mean, I'm not using these in practice. I'm a theoretical computer scientist, so I don't. I don't use these. Okay. Okay. So this is just one slide that is some kind of advertisement from one of these companies called Neo4j. So they're one of the leading companies that sell graph database systems. So this is just one classical database, and they show one way how to simplify it using a graph. So this is a relational model. So each of these boxes represents one table. Okay, so each of these will be one column. And then they show that you can actually, with their system, do it much simpler and view that as a graph. Okay. I mean, well, just so these two things should be equivalent, but one of them is simpler, and yeah, this is what they say. Okay. So now what about queries? And let's go back to our homomorphisms. So if our database is a graph, so now we'll only speak about graph databases. So graphs, meaning directed graphs which have labels on the edges or on the vertices, both can be done. So I can model a query like this. So here is one piece of information I would like to have. So what is that? So this is like a 3-vertex graph. So I'm asking for a person, okay? Basically it's 2 persons. The name, I put a star, means I don't care about the name. So 2 persons who both have the same occupation. Okay. The very basic way to think about this will be just to find copies of that graph. Okay. So it will be what we call in graph theory subgraph isomorphism. So you just want 2 persons having the same. So this is one example. So you have what is it? Jimi Hendrix and Marilyn Monroe. They were both singing. So they are singers, okay? Marilyn Monroe has 2 occupations, okay? She's actor and singer. So there is another answer to that query, okay? It will be this. So when we ask that query to the graph database, we should basically get all these matching pieces of information, okay? So we have these 2. But, well, sometimes we will have some other things. So for example, this is another example, okay? So what is that? Same thing, we have two persons, we don't care about that name. They should have the same occupation, same profession, but we also want to find their country, okay? What country they're citizens of, okay? So what we'll obtain is, for example, this example, again. So we have here Peter Sellers, Marilyn Monroe, they have the same occupation, and yeah, United States and United Kingdom. So we will get that graph. But maybe,
But the countries can be the same also.
well, exactly, this is that examples, that the country can be the same, okay? And this is basically one motivation why we use graph homomorphism, okay? Because if we would just look,
This one couldn't have been found with just subgraphs.
yeah, if you just do subgraph search, you'll not find the second one because you will really look for a subgraph on 5 vertices, right? But actually, we also want this one, which only has 4 vertices. So this is a motivation for why homomorphism is important for that kind of queries in databases, okay? So we want to return both of them. Okay. So, right. So what we so for now, for me, a query in a graph database will just be another small graph, and I want to find the homomorphisms from that graph to my graph database. Okay? So this is exactly the query problem on graph databases, let's say. So what kind of problems do people study? So from the algorithmic point of view, I mean, the first basic problem will be, okay, you're given a graph database, I mean a database in general, and a query, and does there exist a match, so what we call a match of that query, meaning does there exist a homomorphism from that query to that graph, okay? So that's what they call in that community query evaluation problem. Then you can actually ask for some more complicated task is to find all the matches, okay? So that's what we could call the enumerating all the matches, so I can call that enumerative query evaluation problem. So again, I'm given a database, a query, and I want to list all the homomorphisms, okay? From Q to B. So that's the kind of thing that people study. And I want to say a word about what is called a constraint satisfaction problem, because it's an interesting thing that has been studied a lot in that context too. So now I'm thinking, okay, again, I'm going back to structures that are not necessarily graphs. So as you see in the picture, I am still having a set of vertices. But now I allow for relations that can be bigger. So a graph is what? Is a set of vertices with a binary relation, okay? So the edges can be seen as a binary relation, but now I allow even bigger ones, like on this picture, there are ternary relations, and there are unary relations. The blue one is unary, the red one is ternary, so 3, etc. So now I can define homomorphisms from these two, from these kind of structures, okay? So a homomorphism from that structure to that structure will be again an assignment of the vertices from the left to the vertices to the right, and then whenever, for example, 3 vertices are in the black relation, the images should also be in the black relation. So it's a more general kind of homomorphism. And this has been called in the literature for a long time, or this is equivalent, let's say, to what is called the constraint satisfaction problem. It is just given 2 of these structures, does there exist a homomorphism from one to the other? So this is this. And what usually people do is that they like to study the question when you fix the target, okay? You consider it as a constant graph, and you ask from an algorithmic point of view, what is the complexity given an input relational structure S to decide whether there is a homomorphism or not, okay? So think of the 3 coloring problem, for example, where that structure is just a triangle, and you give a graph, ask, does that graph have a homomorphism to that triangle? Okay. Is it 3 colorable? So this is just a generalization. Yeah, so that's what I'm saying. So you fix a graph H, and you're asking, what is the complexity of the following problem? H coloring, I given a graph, is there a homomorphism from G to that graph H? And well, one of the earliest results in that area, so by Helen Eschatrill from 1990, is that for every graph H, we know that the answer to that problem can be done either in polynomial time, or if not, then it will be NP complete. Okay? So the polynomial cases are just when H is a bipartite graph, so that's like two coloring, or when it has a loop, this is like doing nothing. And all the other cases are NP complete, basically.
So their theorem is true for all graphs, right?
Yeah, undirected graphs.
Yeah, it need not be simple. We have loops and all.
Well, the thing is, if you have a loop, it's trivial because every graph has a homomorphism. Okay, so that's polynomial, and if you have parallel edges, they are not necessary. Yeah. But important thing here is undirected. Okay? Because for directed graphs, the story is completely different, actually. It's very complicated for that one. And so when we come back now to higher structures, so let's take these relational structures as I showed you the picture with bigger relations and all. So in the 1990s, Feder and Vardy, they gave this dichotomy conjecture, they called it. And that was to say that the same will be true for all the structures. If you fix one structure T, the corresponding problem will either be polynomial time or NP complete. And for those of you who know a little bit about complexity questions, note that this will not always be the case. I mean, you can have problems which belong to the class NP, but that they can be neither NP complete nor polynomial time. But they're called NP intermediate. So their conjecture is basically to say that there are none of these weird problems. So these homomorphism problems will behave nicely. Either they will be NP complete or polynomial time. And that was actually recently solved. So last year, there were two parallel proofs, independent proofs, by Bulatov and Zhuk. Both appeared at that conference, Fox. And there was a huge amount of work. I mean, this conjecture was very inspiring. It has taken maybe, it has developed a whole field on its own called universal algebra and techniques from algebra to prove complexity results, to prove algorithms. It's a very beautiful topic. Lots of interactions with logic as well. Okay. And finally, last year, all these people working in that field, they finally solved, these two solved the conjecture. But it was based on lots of incremental steps, lots of beautiful theories there. Okay, so I wanted to mention that. And so that, by the way, includes, for example, that conjecture, which is now a theorem, includes, for example, homomorphisms of directed graphs, right? So we know that they're all NP complete or polynomial. However, the characterization is based on algebra, so it's highly non-trivial. It's about counting what they call polymorphisms.
Their proof contains a characterization.
Yeah. We know which are the NP complete and the polynomial examples, but when you look at the graph, it's very difficult to find it. So even for very simple examples like directed cycles, we don't really know, for example, what is the smallest NP complete one. I mean,
What kind of relation structure we can identify, which helps these queries in a graph?
what do you mean?
Go for a query, we look for some specific property, specific kind of graphs we are looking for.
Yeah.
So if it is just an arbitrary graph, I don't see how can we reduce from brute force to something, some kind of intuition if you can give,
Well, I mean, of course, in the general case, if your graph is general enough, you will have an NP complete problem. So it will, as you say, you'll probably need brute force unless P equal NP. But the thing is that you can actually find some nicely structured graphs. I mean, for example, just take some things like that are very used in practice will be some trees, for example,
Right.
directed trees. Okay. And in fact, you can have, there is a lot of, I mean, I will speak a little bit about that if I have time. But there are lots of data or graph databases which have this structure, actually. For example, XML documents. I mean, they are not properly speaking graph databases, but they are another way to view data. They're actually stored like that. So they are actually oriented trees like that.
So do you think it is because of the storing nature or the property of the data?
No, it's about the property, because here everything has this structure that everything goes from top to bottom and there are no cycles.
Okay,
So
properties represent
yes.
represent a particular structure
exactly.
And then it helps to identify that homomorphic.
Yes, yes, exactly, yes. So for some special cases, for example that case, you will have some algorithms, okay? And I mean, that's basically the goal of this whole entire topic, is to identify particular nice cases which are interesting enough, non-trivial.
Structure which we have to find, right?
Well, no, you study one particular class of structures, they have that property, and that property will help you to find the algorithm, right? I mean, that's kind of the goal of this whole thing. Yes, yes. And or the other way, like what properties will always give you some NP completeness, right? So that's the thing. Yeah. I mean, some people may like them more, I don't know. Yeah. Yeah, yeah, yeah. Well, the people doing database in practice, they might avoid them, yes, but.
Transitivity is used heavily for the structure because it looks like more like kind of relation.
Yeah, I don't know too much about that either, so I don't. Okay. So so I wanted to mention that connection to this field, which is very nice also. Let's continue on what kind of question. Okay, by the way, do you know when did I start?
Yeah, you have 10, 15 minutes.
Okay, okay. So one other interesting problem that you can ask. So I give you a query, right? So a graph. And the question is that query minimal? Minimal meaning what? That does it contain a subgraph that has the same properties, in the sense that, let me be more clear. So if I take a query, it could be that actually there is a smaller query that lives inside Q prime that has all the same properties, meaning that for every database B, that if Q goes to B, that also Q prime goes to B. Okay. So that we don't want, because of course this is not optimal. If we take a bigger query, why should we take a bigger one if we can use the smaller one? So this is what's called the query minimization problem. And for people doing graph homomorphism, this you could actually see as testing whether a graph is a core. Right? So finding the core of a graph is actually a problem of minimizing a query for graph databases. Okay. In the same way, you can ask for query equivalence. So given two queries, are they equivalent? Meaning that, again, it could be that for every database B, every time this one goes there, this one also goes there, and vice versa. Okay. So this is another problem that is important in this field.
So given a graph to find a core, is it attractable?
No, that's a co-NP complete problem actually. But again, for some special cases, it could be tractable. Or,
So equivalent means Q1 or Q2 there is a homomorphism.
yeah, you can view this as as having a homomorphism in both ways. And again, query inclusion is just homomorphism in one way. If Q1 is if Q2 is included in Q1, it's when Q1 has a homomorphism to Q2. Okay.
A special case of this is core. Core is this kind of an inclusion, but it has to be a subgraph also.
Yes, but also you don't know Q prime, right? So you're asking, does there exist? So it's a bit different. But. So I'm just showing you these to give you some spirit of what people are studying in graph data or in query and stuff like that, and what kind of word they use. But to show you that this is actually very close to what we know from graph homomorphisms. Okay, another example that I will just show you also for another illustration is what people call database repair problem. So you have a database, but you know it is broken. And then you have a family of queries, Q1 to Qn. So you want to modify your database in a minimal way such that it will answer all these queries, because you know that supposedly it should be matching all these queries. Okay, so this is what people call query constraint answering. But actually we can view it as a graph modification problem. So you have a graph property P, and you want to modify the graph, like remove some edges, maybe some vertices, so that it satisfies your property. So again, this is a connection between the two universes of databases and graphs, And this problem is very, very studied, actually. Lots of people look at that. Just another example. Okay, but now I want to show you some new type of queries. So that was all for, let's say, standard homomorphisms. But now I want to show you a new type of queries, which has appeared in practice in lots of applications, which is called navigational queries. So in the graph homomorphism, in some sense, we have some locality involved, in the sense that when you have a homomorphism from Q to B, well, what you know is that the part of the database that you will, have that homomorphism, well, would be small. It will be as small as that graph Q was, right? But sometimes we might want to be able to find some connections which are very large compared to Q. So this is how it can be. Okay. What is this? Yes. So remember that same example I showed you. So we had these two persons. We looked at the same profession and what are their countries and all. So now we could express some new type of queries. So now I have some new type of edges, which I put in that wriggled shape. And that, what does it mean? So I have a person, its profession, its city, I mean place of birth. So in that graph, as you can see, there are lots of professions which are actually subclass of other professions. So for example, musician, singer is a subclass of musician, and a musician is an artist, etc. Okay, so you have some hierarchical relation like that. And the city, well, a city is part of maybe of a state, like Seattle is part of Washington, which itself is part of a country. What I mean is that in that precise databases, the relations are not maybe just ancestry relation, I mean just successor relations. They are maybe actually connected by a long path. So these wriggles here actually denote a path. So now a match from this query can have arbitrarily long path along these edges. Okay, so this is one example. So as you see, this actually has 6 vertices, but the query has only 5. This is another example because you have these long paths that connect the nodes of interest of you. Okay. So that's the example. So what is a navigational homomorphism? Again, it's very similar to homomorphism, except that on the graph on the left, on the query graph, instead of having labels, you will have sets of words. So what is a word? So, okay, to be more abstract, we suppose that we have an alphabet, sigma, A, B, C, D, blah, blah, blah. So these will be my labels on the graph, like you can see here. So that's my graph database. And now, on the query graph, so that one on the left, you'll have sets of words of labels. So for example, this set of 2, so AAB, AAAB. What do they denote? They denote the possible labels of the path that you can map to. So this wriggled edge here, it can map to 2 vertices that can be as far as you like, as long as the path, or some path that connects them, has the labels in that set. Okay. So in that case here, AAB works, because this has AAB. Okay. So this is what we call navigational homomorphism. I said path, but what I mean actually is walks, because we could have repetitions. I mean, anything is possible. You can restrict to path, you can restrict to walks, as you wish. Yeah, and so this has been actually used by people doing graph databases. In practice, they actually use this kind of navigational homomorphisms. One big class of navigational homomorphisms, it's based on what is called regular languages. So for those who have done computer science, they will be familiar with that. But I will not go too much into the detail, but what is a regular language? It is a way to define these words I told you about. And it is a very nice way that is well studied. It has a very beautiful theory behind it. This is studied by every undergraduate in computer science. And for those who don't know about it, I encourage you to study that. It's very beautiful. So regular languages are those, so you fix an alphabet, and you will find a set of words, And that set of words should be closed under some operations, which are 3 operations. The union, which is plus, the concatenations, so 2 words, you can glue them together, and what is called the clean star, which is some kind of inductive repetition of a word. So a word with a star will mean that you can have any arbitrary number of concatenations of that same word. And when you look at the closure of these 3 operations over elements of your alphabet, you get what is called the regular languages. You can express them using what is called regular expressions. So this is just the string that I've given an example. So it's just the operations on that. And it turns out that regular languages, so these sets of words, are exactly those words or sets of words that are recognized by what is called a finite automaton. So finite automaton is actually just a labeled digraph. So again, digraphs, where the labels are these elements of the language. I mean, I will not go into the details, but basically why people study that is because it is well understood. It has a lot of theory behind it, and still it is very expressive. You can express lots of words using that and languages, but still it is well understood and we know what to do with that. So now when I come back to my homomorphism, one of the main things which has been studied is when these sets of words are basically corresponds to these regular languages that I just explained. Okay? And they are called regular path queries, RPQ. So there is lots of literature on that in that special case. Okay. So now if we come back to that basic problem of query evaluation, so we are given a database B and a query Q, which is one of these regular graph queries, and the question is, does there exist a homomorphism of that kind? Okay. And this was defined last year as a problem by these 3 authors, Barcelo, Romero, and Vardy, and they actually gave a complete NP-complete and polynomial time dichotomy, which uses that dichotomy theorem that I told you about earlier. So these are very recent results. So this is when we have a database, a query Q and a database B. So basically, everything is known. I mean, in some sense, lots is known about that.
So they did it before.
This was last.
The conjecture?
Yeah. I mean, even actually when they wrote the paper, the conjecture was claimed to be proved, but there was no publication yet. But they said, yes, if the conjecture is true, then this is true. They gave an equivalence between the two. Okay, good. But now, then last year we saw this and we thought, what happens for 2 queries? Because what I just said, I mean, maybe you noticed or not, but we have now these queries and we have database. So the database still has only these simple labels, right? These A. But now the query is more complicated. It has some sets, right? Okay, sets of words, like, etc. These sets can be infinite, by the way. So in my case, these sets correspond to regular languages. But now you could actually ask a homomorphism between 2 queries. I don't have the brush. So now you could actually put complicated labels on both sides of the homomorphisms. Okay? This is to know that if a query is included in another one. So that's actually much more complicated. But we can define some type of homomorphism also between these 2. So here the definition will change slightly, but we have to think a little bit how to define it properly. But again, when we have an arc with this label, it will match in that query again to a walk. Okay, so if that was x, y, it will match to this walk. But now we don't have labels, so it doesn't make sense to define a word on that should be in that. So what we take is that we actually take the concatenation of all these sets here, okay, and we say that this new big set that we have should be included in that set. So it's based on set inclusion. So it's a bit more complicated, but it greatly models this inclusion of 2 queries. So then we ask ourselves, what is the complexity of that problem? So this is what I would call homomorphism-based query inclusion. RPQ inclusion, regular query inclusion. And actually this is not even in NP, so this is much more complicated. This is very easily shown to be p-space hard. So p-space is a complexity class which is above NP. But we gave an algorithm which works in exponential time. So at first, actually, it was not even clear whether there exists any algorithm for that problem. I mean, we didn't know if that is decidable. So we were able to give an algorithm in finite time, which is exponential time. But still, we don't know what is the right complexity. Is it polynomial space or is it exponential time? What is the exact bound? We don't know. Okay. Well, I will skip that. Okay. But this is the very general problem. I mean, it's very interesting, but it's very general. It's very expressive and all. But now you could ask some very particular special cases. And one case which I want to highlight, because that could be studied more easily by graph theorists, is when for example, your alphabet is only one letter, only A. Okay? Like remember, the classical graph homomorphism is, in some sense, it's like that. Like you could say that every edge has the same color, has A, and then you're just asking for homomorphism. For an edge labeled A should go to A. And one of them, which is actually used in practice quite a lot, again, it's related to this, where's the brush? Oh, it's there. To these XML things I told you about, is when you only have two types of labels, those being either A or A plus. What is A plus? This will be the set A, etc. So it's an infinite set that basically says you can have any walk of edges, okay? So this is fine, okay? A is good. So now you can imagine that some of your edges have A, some of your edges have A plus, and the same in the second graph. Some of your edges have A and A plus. So what it says is that these edges have to go to an edge, but these edges have to go to any path or any walk, actually. So they have to connect some connected vertices. So that's the problem.
Doesn't say anything about the length of it.
Doesn't say anything about the length in that one.
Big can go to small, anyway.
Well, these can go anywhere, but these can only go to a 1. Yeah. And so that one behaves again more nicely because again it is between polynomial and NP complete. So when you do these very simple ones, you don't go to these higher exponential classes. It's polynomial and NP complete. But still, finding which ones are polynomial and which ones are NP complete is still an interesting problem. So for example, when you do undirected graphs, actually you can do the same as this Hell-and-Nature trill. I will skip that. So undirected graphs are very easy because connectivity goes in both ways. We don't have arcs. So it's actually a bit trivial. But the interesting case is when you have directed graphs or oriented graphs, right? Because now you have arcs like that. And an arc labeled A+, it can go to something like that, but of course it cannot use reverse arcs, okay? So you cannot go anywhere in the graph. So that becomes more interesting. And we have studied that one. And we studied the case when that one on the right is just a path, directed path. And that we found out it's always polynomial. But the general case, even when it is a tree, like that one, top to bottom, we don't know, actually. We don't know the answer. So even that is interesting already. Okay, and the last thing I want to mention is, okay, yet another problem. So I didn't mention it, but it turns out that this query inclusion using homomorphisms is not fully describing query inclusion, actually. What I mean is that you can have two queries, Q1 and Q2, in the same model. That they are included one in another, meaning that for every time this one has a match here, this one will have a match also. However, it can be that there is no homomorphism, like that. Meaning that definitely if there is a homomorphism, there is inclusion, but the reverse is not true. So this is a very strong, homomorphisms in that sense are a strong way to model query inclusion. This behavior does not appear in the traditional homomorphisms, but now when we use these complicated labels and all, this behavior can happen. And there have been entire papers in the community of database things devoted to finding that answer for trees. So these are trees, top-down oriented trees, okay? I mean, the arcs are not there. These double edges are modeling A+, and the normal edges are A. And I mean, this is just a picture coming from their paper. And they show that there is a tree of order 31, I mean, two trees, that they give equivalent queries, but they are not homomorphic. I mean, one of them is homomorphic in one side, but not in the other side. So again, this just to show you that this is another type of problems that can be studied. Because when I saw this, I thought, okay, well, trees of size 31 and all, maybe we can find actually a smaller example, right? It could be interesting to find what is the smallest one which has this property. So this is again a pure graph theoretic, homomorphism-based question.
Is the smallest one known till now?
Yeah, yeah. So this is again appeared in 2017. So this is very recent.
And are there something known that until this much everything is?
No, not really. I mean, these people are more computer science based, so they will not really care about these questions. What they did is that they just wanted one example because there was a conjecture that this does not exist. And these guys actually proved the conjecture is wrong by giving this example. So apparently the story goes, because they wrote that in some paper, because some professor was very happy that they proved this. And then these guys, when they announced it, they actually printed a T-shirt with that example. I mean, apparently this was a big thing in the community. So they came to that conference wearing this T-shirt with this tree. So.
So if we can solve it, we can make T-shirts.
Exactly. Maybe. Maybe. Okay, so that's all. I just wanted to give you an overview of this whole topic and give maybe some ideas. So the main thing I want you to remember is that, okay, basically when we do things with graph homomorphisms, basically it usually corresponds to a problem in database theory. And looking at these papers, what these people are interested in, we can actually take some problems which are also interesting for us that will be interesting for them as well. So here are the questions that are left open from that talk. I mean, we didn't do much of work. There's lots of things to do still for those interested. So as I told you, that this general complexity of the problem of query inclusion by graph homomorphisms, we don't know the exact complexity. Is it exponential time or is it less? For directed trees, still the problem is open also for the complexity. This is the last one I presented to you, to these two trees. Can you find a smaller example? Yeah, other things maybe you can think about. That's it, thanks.
So, in the homomorphism, the complexity related questions, people will be also interested in like sub-exponential time algorithms, parameterized algorithms also, right? Have there been their studies in that direction?
I don't know really. I mean, of course it is interesting for me it will be interesting as an algorithmician. For the people doing actual graph databases, I don't know, because that I don't know. But in general, yes, it is interesting, yes.
I have a nice question. Homomorphism to a homomorphism help in query of geometric database?
I don't know. So do you mean geometry being that it's a graph?
Geometry, and then they have a relation and see whether homomorphism works there. Any idea?
I have no idea about that. I don't know.
So the homomorphism of geometric graphs, like planar graph, which is also a geometric graph.
Yes.
Does it have homomorphism, any kind of query of those?
Well, yeah, I mean, people doing the usual homomorphism problem, they study planar graphs sometimes. Because having a planar graph as an input, for example, can reduce the difficulty. Just to give you an example, if you ask for what is the complexity of deciding if a planar graph goes to a triangle, 3 coloring, well, this is actually NP-complete, but if you come now to the K4, this is polynomial, because the 4-color theorem says that it will always be yes. So that shows that it can be easier, and it's actually still a major problem to determine which ones are still NP-complete and which are not.
Oh.
there's some work in the topic, but it's actually very difficult to find. Yeah, it is.
What are the easier problems here?
Well, the ones I pointed out, I think
They're much more,
they're more tractable, yes. But
one can try.
yeah, one can try, or at least one can, because you see the nice thing there is that even if the general case is difficult, there are very nice subclasses and structured. I mean, like these directed trees, you know, you could even impose some further conditions, and still it will be interesting, you know.
Oh, that's
So there is a lot of things that.
Only for directed trees, directed path.
Yes, I mean directed path. For example, we showed that it's always polynomial.
A plus.
Yeah, AA plus. But of course you could then, well, another thing I did not mention, but you could just, AA plus is very restricted, you know. You could have, actually what you said was also interesting. This is another, I should have put it in my talk, I forgot. But you could imagine that all of them are of that form. AK, A to the K, meaning just a path of length A. So if an edge will be like that, that basically means that it has to go to a path of length exactly K. So this is like putting some weights in some sense. Like you could, yeah, or at most, or you could put at most, you know. I mean, you can imagine all sorts of applications that will fit in this language, and it could be very interesting on its own to study this kind of homomorphisms.
Something like L1, 1, 1.
Yeah, I don't know about that, but maybe. So, lots of things to discuss.